let's start then, and they can join us anytime. They also, if you're recording, they can always follow the recording. Okay, today we have 3 files. I'll try to go over them, but if we cannot reach it to next week, we shouldn't have a very long session. So if there is something missing this week, we can move it to next week. All right. So data science, machine learning. Today's lecture is about using different algorithms, machine learning algorithms, to try to predict data. And machine learning is the branch of artificial intelligence that tries that uses data to through automatic algorithms extract the insight of that data to be able to predict new outcomes of new data that we have not seen before. Okay, so that's basically what machine learning does. And there's different, those that went over the link that I sent, there's different ways of doing that. There's different algorithms, that not just one. There's several of them. And luckily, as in many other areas in Python, we have libraries that do that for us, and we don't have to take care about all the design of algorithms, which is not easy. And all we can do is just grab one of those libraries and use those algorithms, the basics of them, and if we want to learn more, we can jump into the documentation of the library and try to tweak here and there and play a bit more deeper into whatever we were trying to do. So today we're going to start with the process. Basically, what you do when you're dealing with a machine learning process or project is that those are the steps that you go. Sometimes you don't need to go through all of them, but basically you have to import the data, whatever the data it is. You have to clean it, as always. In the event there is blank spaces on the data, there is redundant data, so you have to clean it and prepare it. Then usually, and we're not going to do it in this very first test, but we'll see it later on the other examples, you split the data to have some data to train your model and some data to test it. Then you create a model to use this data. In this case, we basically get it from the library that we're going to be using from Python. You train the model with the data that you have. After you train it, the model is going to be able to make predictions. And after you make predictions, you usually want to evaluate those predictions and be able to tweak and improve the model, because the model has several parameters. So it's not like we have a beautiful machine that we send our data there and we're going to have a great outcome. In part is that, but that model works with different parameters, and that's where the value of whoever understands the technology is, because with experience you can figure out, if I tweak this parameter here or I tweak this parameter there, I'm going to get a better outcome. And I measure, if I see improvement, I just have an improved model already there. So this is an iteration process. So as usual, and for this first notebook, we need to use a data set, a very simple data set that it's also there on GitHub, that it's called music.csv. It's a very short file. And what we're going to do is we're going to try to figure out what type of music genre people likes, okay, out of a little simple data set that we'll be using, which is this music.csv file. So as usual, the first thing we do, here, let me open up here and upload the file. So as this, I need the little, there we go, icon to appear. I click here to upload, and there it is, my music file. I upload it. It warns me that it's going to be disappearing after I close the session, and there it is. Okay. If you're using your local machine Anaconda version, you just have to upload it there on the same place where you have the notebook, and it will just grab it from there. Okay, so once we have the file, I'll just start. I import my pandas library and identify it with PD, just a short, and I'm gonna go through all these processes. I'm gonna go through point number one, import data. Okay, we're using the music data frame, the music CSV file that we imported, and we're gonna create a data frame that we're gonna call music data, importing that file, and that's what we do in this first cell of code. And I just type the name here to print it, and as you can see, basically we have 18 pieces of information or records with the age, the gender, with 1 represents male and 0 represents female, and then the music genre that defines that males from 20 years of age like hip hop, 23 years of age like hip hop. You notice that we don't have 22 years of age, 25 years of age like hip hop. Then other ones like classic jazz music, and the seniors, let's call them, from 30 to 37 like classical. And the same for women. The younger ones like dance music, the mid-range age like acoustic music, and the older ones like classical music. So we have a very short amount of information file that defines that for us. And we're gonna use that information to try to figure out what someone, a male of 21 years of age, as we expect, should like hip hop music, because it's in between these two. Okay, if we go to a male that's 27 or 28, he should like jazz. Okay, and if we go to a female that's let's say 28, she should like acoustic. That's what we expect from all these processes that we're going to be running here. So once we have the data important, we clean it and prepare it. Here we don't have to clean it. It's already clean for us. There's all the numbers or all the information is there. One thing you gotta know is that when we're dealing with all these algorithms, we need all the columns to be usually, not in this one, but usually we need all, there's some terminology here. The variables that we use are called the features. Okay, some people also call them variables, but we are going to be using the age and the gender to determine the outcome. The outcome is called the label. Okay, it's what we are expecting to predict. Now, all the features in all these algorithms have to be numbers. That is the reason why we are using 1 to identify males and 0 to identify females. If we write down here male, 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 and female, it's not going to work. We need numbers there. So we always need to represent any feature with a code if it's not a number. In this case, gender is not a number, so we use the code to represent it. Okay, so once we have cleaned the data, which in this case we have it, we're going to prepare it. And basically what we need to do is we need to see to make, split the data between the features and the result, the outcome. And by convention, we use the capital X to write in all the data with the features. And basically what we're getting here is all the columns except for the genre. This data drop. What does for us, it drops the columns that we add here. So we need on features the 2 initial columns, which are all of them except for the outcome or the label, which is the genre. And for the Y, we're going to get all the data from just this column, the genre column. So if we run this, we already have this information here. I can type the X here, and it's going to show me that the X is a matrix with 2 columns because we have 2 features. We could have had more features like the height, the city where they are from, whatever we want to add here. The more we have initially, the better, although there's also a technique to choose which features are really needed and which are not, because they are redundant or we don't need them. They don't represent any valuable information for the model, but that's another issue here. So we have the X data frame with all the records and the two features. And if instead of the X I type here the lowercase y, I'm going to get a vector, in this case just one column, with the outcome. Okay? All right, now that we have the information the way we need it, now we're going to call our library here. And the library is Scikit-Learn. It's a machine learning library. It's one of the most known and the most used, although there are others. And here you can click here and go to check the documentation. One of the beauties of Scikit-Learn is that there is a lot of documentation. It's a great documented library. And if I just want to jump there, these are all different algorithms to try to work, to use. Okay, there's classification algorithms, there's regression, there's clustering, there's dimensional reduction. These are basically tools to reduce the amount of features. Imagine that we want to know how many crimes are on a city, getting the amount of population, getting the amount of, I don't know, of different, the percentage of races that are on that city, the amount of youngs against olds, I don't know, the income, the average income of that city, several features. So the dimensional reduction is all the tools that we use to try to reduce some of those features, because right now we're working with only 17 or 18 rows of information, but as you can imagine, we need hundreds and thousands of data to try to get as much accurate as possible on our models, all right? And the more data we have, the more it's going to take the model to get trained and get all the rules and all the insight from that data to give us later on predictions, okay? So that's one of the beauties of Scikit-Learn. It's very well documented. And that's what we do here. Usually with Scikit-Learn, instead of what we do with other libraries, that we import all the modules on that library, in Scikit-Learn, the common use is just to upload the module that we need. In this case, we're gonna upload a machine learning module that is called tree. It's a decision tree that we're gonna be using in this first notebook. And we import the decision tree classifier function from the model tree in the Scikit-Learn library. Okay, that's what we do here. And we're gonna create the model. And basically we create the model just adding a variable to this function. Okay, that's what we do here. And if we run this, you're gonna see, so it just, it's not showing here. It will show in the other, if I type here model, just to show you, well, what it's gonna show me basically is all the parameters that this function can be, all the parameters we can use to tweak this algorithm, which is the decision tree classifier. Okay. Now you see the word classifier here. There's in machine learning there is two types of problems basically. There's some other, but basically there is two main classes of problems. There are classification problems and regression problems. Now with classification problems, what we try to do is to put on a group of, get an outcome of some data and decide which group is this data going. Like for instance, a very common classification problem is the spam is to measure if an email is spam or not spam. It's called classification because we are trying to classify that email into just two categories. One if it's spam and zero if it's not spam, which is also called ham. Okay, so that's a typical classification problem. If I want from the other side, if I wanna predict from different kids getting their city, getting their weight, and getting their age, and I want to predict their height, that's a regression problem because the outcome is a number, is a real number. It's not 1, 2, or 3. Okay, so that's basically two big categories of machine learning problems. In this class today, we're gonna be dealing with classification problems. All right, so again here, not that you have to know them, but these are all the parameters that we can play with to try to make little changes on this specific algorithm, the decision tree classifier, to try to get a better outcome if we are not happy with the result we get when we test it, okay? Now, once we have the model, all we have to do is train it, is use all the data that we have to train that model and try to create the rules to make predictions. And this is what we do here, okay? We training the model, it's done with this function, which is called fit, and we added the X variables, which are the features, the ages, and the genders, and the Y label, the Y data frame, which is just one column, and it's the labels of those features. And we just train the model, okay? And well, this is giving us just the music data. It doesn't need to show here because this is just the original music data. Okay, and now that we have trained the model, we can start making predictions, okay? And we can make predictions of as many values as we want. All we have to do is add the array of values inside the brackets of the predict function of the model that we instantiated here when we created this decision tree model. So in this piece of code, what we're going to ask is to make predictions of two values: a male that is 21 years old and a female that is 22 years old, okay? And check the outcome. All right, now yeah, I know what we had here. We had why we had here the music data, because we can check if we run it, we can check if we are predicting correctly, okay? So now if I run the prediction and I print it, if we check, a male of 21 years old is right here, so it should be liking hip hop, and a female of 22 years old, it's right here, and it should be liking dance. So if our model does a good job, we should be getting hip hop and dance as the outcome. Let's see what he does. Hip hop and dance. Okay, so we can say that initially this model is doing a good job predicting what we expected. Okay, now we're using a very reduced sample and just testing with two elements or two options. Okay, now we gotta, when we try to create the models and tweak it and tweak them, we want our model to call to do what it's called generalize. By generalize means that it can predict well any kind of information. In this case, as you saw, we checked information that it was inside the amount of data that we had. But what may happen if we, instead of 21 here, we write down here, we put a 40 years old male and see what it says. Okay, it's still giving us classical, which is what we expected, because the older ones like classical music. Okay, so those are things that we want to check once we have our model trained and we are starting to give it values to make predictions. Okay, now usually when we do is to get our data and split it, and from all the information that we have on the data frame, we use some of those records to train our model and keep the rest just to test how good that model does. Because if we keep some records to test, we know the outcome. So we can predict the outcome once the model is already fit or trained, and check those predictions against the real data that we have because we save those records just for testing. And this is what usually we do, okay? And this is what we do. There's this function on the Scikit-Learn, which is model selection, and from the model selection module, we extract the function train test split, okay? And this little piece of code, this is one of the beauties of Python. You can add a bunch of variables in front of an equal sign, and the outcome of this function is 4 groups of data frames. It's gonna this little piece of function, it splits our 2 data frames, capital X and lowercase y, into 2 blocks of size. One is going to be 0.8 and the other going to be is 0.2. So if we have, let's say we had 10 instead of 18, I think we have. If we had 10, we would have the test group with 8 elements, or excuse me, the train group with 8 elements or 8 samples, and the test with 2 of them. Okay, since we have 18, it's going to be a little bit more than that. So this is what this function does. All right, so we split it. Once we split it, we train the model just with the train values. Okay, we leave apart those values that we want to use for testing. And then we make predictions. Once we've trained our module, we make predictions with the test values that we have. And this is what this line of code does. And once we have the predictions with the test values, we use those tests and we measure the values that we got predicted from the test values with the real outcome that we have from the test values that we kept apart. And we measure, okay? A way to measure is also another function from the Scikit-Learn, which is on the metrics module, and it's called accuracy score. And what we do is right here, we generate a variable and we give it the value that we get from this accuracy score function between the test values that we had and the predictions that we get from the test variable, from the features of the test values from the split that we created here. And finally, we get a score, okay? So that's what we do here. And the score we get, of course, it's a variable between 0 and 1, meaning 1 is that our model predicts perfectly or made a perfect job predicting, okay? So this is usually the process to measure one of the processes, the most common one, which is the squared error. It's called the squared error, but there's others that measures the accuracy of our model, okay? So again, we have the tools, we have the algorithms, but we need the human intervention to adjust and to make sure, measure and to make sure if this was instead of a 1 was a 0.3, we know that our method was predicting really, really bad, and we would need to tweak it. In this case, it wouldn't have much sense because the amount of data that we're using, it's very, very, very small. But instead of 18 records, we'd had thousands of records, and we were getting a 0.3. It means that we are really doing a bad job with this algorithm. We would need to start tweaking it here and there. Now, one of the beauties of Scikit-Learn is that imagine that we are doing this with thousands of records, and it takes, I don't know, a day or hours to, train our model with all this data and finally get the model trained. One thing we can do is use this module from Scikit-Learn, which is called externals, and create a little piece of code that basically is a file with all the parameters needed to make predictions. So this is called persistence, and this is what's doing here, and this is creating me, hopefully, if we go here, there we go, music recommender joblib. This joblib is the extension that this dump function that we gave to this dump function created for us. So after that, another day we can just go and get the model instead of create the model from training as we did here, model.fit. We already have the model. So what we do is we get a variable that we're going to call model here, and we upload from our file the joblib file that we created previously some other day, and then we make predictions. And if we run this, you will see that we'll get hip hop and dance again. Okay, so there's this tool that right here doesn't have much sense because you saw that we went real quick to make predictions, but once you start working with a big chunks of data, this is a very interesting way of saving time once you've trained your model. And there is no additional data that you can use. What usually happens in these problems, in these machine learning problems, is that you keep, as you can imagine I don't know, an e-store, you know, an e-shop that keeps getting data from customers. So if you want to have a recommender, you want to get all the new data to train again your model and to get more accuracy into your predictions. So usually you run you may get, you know, thousands of records. So maybe what you do is you run your training model once a week, and after you have that, you create the joblib file here, and then use it to make predictions real time when new shoppers are coming to the shop. Okay. By the way, I don't know if you guys are seeing my cursor. I forgot to activate that cursor thing that I used the other day. Do you see the cursor on my screen? Hello?
No, I cannot see the cursor.
Yeah, let me just real quick. Let me get this.
Put it with yellow, I think, or something.
I think, is it here? This little thing that I had here the other day, the screen pointer. There we go. Do you see it now?
Yeah, perfect.
Okay.
Perfect.
Sorry, I forgot to activate that. Okay, so this is a way to persist our model, our trained model, once we've created. Okay, finally, for this first exercise, remember that we are using a decision tree algorithm to model our, to use with our data to predict. Okay, now decision tree is a kind of algorithm that basically uses grabs our data and creates a bunch of rules, and you can, it's one of the few that you can have let's say a representation of the algorithm. This is what we're going to do with this function. You don't have to understand this function, but basically what we're going to do is we're going to dump or create a new file that we're going to be calling music recommender ... Okay, and once we had that creates a type of file that we can actually see. And if we finally get this this file created, we should be able to get it here if it runs. Let's see if it appears here, because I wanted to show you. And you can see these type of files in most of the development environments that are out there. Let me run it again, because there we go. The dot. But I just added here here we go. Let me grab this here. Oops, I had here something on my, oh jeez, I ruined it. I changed these, I changed this this URL here that was here, and for whatever reason I ruined it. I wanted to show you here. Let me see if I can find it. What was it? Let me check. Can someone share this little last line of of code with the URL that was showing here on the Morphosis channel, so I can grab it.
Like the URL.
The URL that's
okay, I can check.
one.
I can check.
Yeah, the one down there, because
Okay.
for whatever reason I messed up.
You
No, not this bit.ly. You should see it here. It's not the bit.ly. It's the one that you see here on your file.
The long. So we're looking
Yeah,
for the long
yeah,
one.
the long one.
I
yeah,
posted it
one.
in the Morphosis channel. It should be there.
Okay, let me go check it there and get it. There we go. Is it this one? Yeah, there we go. Okay. Now this is just an online visualizer that we can use, and there we go here. Okay, and basically what we do is here is just we delete all this data here. Okay, and we go to our file, and if we let me see if this is gonna open. No, oh, it's downloading it. Well, I just open it with the open with. Let's see what it's gonna be with. There we go. So we just grab all this data. We copy it and we just paste it in this visualizer, and there we go. It shows us this decision tree. Okay, now let's go over this decision tree so you get the point of what this algorithm is doing. Okay, basically it's defining the boundaries of the different information, the boundaries of the different genres that he understood from the data that was being on that data file that we used. Okay, so basically if we go and check the data, we had all these ages here, and what the graph shows, it tells us, okay, it checks the age, and it says if the age is below 30.5, which is basically 31, because we have whole numbers only for the age. If it's below 31, if it's true, I'm going to go in this direction. If it's false, so if it's older than 31, I'm telling you that it's classical music, the outcome. So if we go check our data, if we see at 31 female and at 31 male, they all like classical music. Okay, so this is the first decision that the graph is showing us. Older than 31 or older than 30, you can already label them as classical music. Now, if they are younger than 30, if they are smaller than 30.5, which means they are 30 or younger, let's check if they are younger than 25. Okay, if they are younger than 25, I have to check again if their gender is smaller than 0.5. Smaller than 0.5 means that zero is women, remember? And smaller than 0.5, if it's smaller than 0.5, which means is women, and is younger than 25, is dance music. And if it's a male and it's younger than 25, he likes hip hop. And those, if we check again, are the younger ones. Males were hip hop, and females were dance music. And then the final decision is that they are older than 25. But if they are older than 25, if we are here, they are already younger than 30, so they are in between. And if they are male, they are gonna like acoustic, and if they are female, they're gonna like jazz. So we'll check if they are male. Oh, it's the opposite. Male is jazz and women is acoustic. So if they are 0, which is less than 0.5, 0 is women, likes acoustic, and bigger than 0.5, which means 1 is jazz. Okay, so this is one of the additional information that we can get with algorithms called decision trees. They give us a nice representation of there's other values. Basically, this is telling us which values of the set it's using to make these decisions here and there, basically. But just with the first line, you get the point of how the algorithm is taking decisions upon the two features, which were age and gender. Okay, initially it uses age, and then it uses gender. Okay, to finally give us what are the leaves that these are, these 5 numbers or these 5. And close this one here, and let's go here. This one, I'm gonna go to lecture B, 4B, and let's work with real data. Okay, now we're gonna be using with one of the most common data sets, which is called the iris data set. And the iris data set, it's already in the Scikit-Learn, and we can just upload it from there. And basically it's a collection of 150 flowers, iris flowers, of 3 species. Okay, we have 150 samples of 3 species, which are we'll check the names there. I think are I forgot the names. We'll check them here. There's 3: Setosa, versicolor, and virginica. Let me go back again. There we are. I'll show you how to see the different species here. But there are 150 samples, and basically these samples, there was this professional that when he created this data set, and they were grabbing these 150 samples, and they were measuring the length and the width of the sepals and the length of the width of the petals. And from that, they were predicting, or they were trying to create a model to predict which type of iris flower was, if it was, which type of species of the 3 of them was. Okay, so this kind of product or data machine learning problem is a supervised learning machine learning problem. By supervised, it means that we have the information that we want to predict. We have a bunch of data with the measurements, which are the features, and the labels, which is the outcome. If we didn't have the outcomes, it would be an unsupervised problem, which means that we don't know the outcome, and since we don't know the outcome, what we try to do with this data is try to classify it. Okay, imagine that we have a bunch of shoppers, and we don't know anything else but just the age and the amount of money that they spend on our e-shop. We could put all that information on one of the algorithms of data, of machine learning algorithms, and try to find groups of customers. And we would probably find a group that's younger, and then we'd find middle age, and then we'd find seniors. Okay, but we don't have an outcome. We cannot tell this specific customer that we have the amount of money that spent and the age. If we have the age, of course we know which group is, but let's say we know which products or how many times it comes, it's been on the shop, and how much money it's spent. From those 2 features, we could try to figure out if it's a senior, a middle age, or a junior or a younger client. Okay, we don't look for the outcome, but we try to classify. Those are unsupervised problems. We're going to be dealing just with supervised problems in today. So since we have the outcome of the 3 species, which species every sample, we have a supervised problem. And this problem just is from the University of California, Irvine repository, and I've given you here the link where you can find the information about the repository. I don't know, yeah, it works. Let's go click it so you can have a look. There's other data sets on this repository, but basically this is the iris data set, okay? And here it's the creator of the data set and the donor, and basically the information. It tells us the attribute information or the feature information. It's the sepal length, the sepal width in centimeters, the petal length, the petal width, and finally the class, which is the outcome or the label. There's 3 classes: setosa, versicolor, and virginica. Okay, that's a little description of the data frame. Now, as always, what we do, remember, the first thing was with the library or the module of the Scikit-Learn library that has this data set. I'm going to just actually load the data with this load function. And I'm going to show you the data type that this data frame is. These data frames are a data type of bunch, which is the specific data frame that, as you can see here, Scikit-Learn utilitarians bunch. This is a data frame created by Scikit-Learn. Okay, and now I'm just going to print the data. And as you can see here, we have all the 150 records of data. The very first measurement is the sepal height and width, and the petal, or vice versa, I don't know, I have to check. Okay, and finally we have this is the data. Yeah, this is the data. So we're having here 4 columns. All we have here are the features. Okay, so one of the way the data is structured on this bunch data type is that we have a separate, we can separate easily the information between the features and the labels. Now, if we want to know the names with once we've uploaded in Iris, in our variable Iris, all the data, iris.feature names is going to give us, you can see it already here, the names of the features. Okay, the first number was the sepal length, the second the sepal width, the third the petal length, and the fourth the petal width. Okay, and now on iris.target, what we have is the vector, and it's a vector because we have only one column, remember, of all the labels. And as you can see, label number 0, if we don't know, see, as you can see, they're right now, they've codified in codes instead of letters our label. Okay, and if we want to know what these numbers correspond to, we have the function iris.targetNames that's going to tell us exactly. Okay, the first one is setosa, the second one is versicolor, and the third one is virginica. So 0 corresponds to setosa, 1 corresponds to versicolor, and 2 corresponds to virginica. Okay, so these types of problems, each value we are predicting is a response, as I told you, or a label or a target of outcome. Okay, it's a supervised learning problem because we already know the response of the categories or the features, and it's a regression. It's supervised learning because the response is ordered and continuous. If it was a regression, the response would be ordered and continuous. Since it's not ordered and continuous, it's just codes that we're using to define which outcome, which type of flower is, with a species. We are here dealing with a classification problem. Okay, now Scikit-Learn requires always 4 things to use their modules, their algorithms. One is that the features and the response have to be separate objects. Okay, if you recall in the previous exercise, we created the X variable as our features variable with all the features, and we had the lowercase y as the response variables. Okay, so we need to have both those in 2 separate objects or variables. Now they should be numeric. Okay, and the features and response should be NumPy arrays. Remember that we used to upload the NumPy library. We don't need to upload it if we're dealing with Scikit-Learn, and this data frame that we're getting, it's already using NumPy arrays, okay? But if we are dealing with some other data, we have to make sure that the data that we are using uses the data type of a NumPy data type array. And if it doesn't, we have to convert it, okay? Otherwise, it won't work on these modules for Scikit-Learn that we're using. And finally, the features and the response should have specific shapes. Remember that shape is the word that we use to define the dimension of the data frame that we're dealing with. Okay, so let's check if let's check here the features and the response, and let's check if they are NumPy arrays. As you can see, if I print the type of our data and the type of our target, which is where we posted or we added up here the data and the target, all the data, they are both NumPy arrays. Okay, so we're fine here. And now let's check the shape. If we check the shape of the data, we see that it's a matrix of 150 rows, which are all the records, and 4 columns, which are the 4 measurements that we're using in this data, which is the height and width of the sepal and height of width of the petal. Now, if we want to work with this algorithm, we need that the target data has 1 column. Remember, it's just 1 column, but the same amount of records. If we, instead of 150 in our target, we have 140, it's not going to work. So let's check it, and of course we created that and we know that it's 150. But those are things that it's good to check, because right now we're using with a very common data set that's prepared to do this. All right, but when you're working with real data, you got to make sure that the shapes have the values that they have to have. No matter if we have 50 instead of 150, but if we have 50 on the data, we need 50 on the labels. 50 on the features, we gotta have 50 on the labels. Okay. Now that we are sure and that we have checked, we can create, and just by convention, put our features data frame into the capital X value. And we don't have to do this, but it's just by convention. If you check any other notebook from any other author just dealing with machine learning on Scikit-Learn, you will see that they all do this as convention. And the Y, the outcome, we're gonna just add the values from the target. Okay, this is what we do here. And now we have everything ready to start with another, whatever we want, another classification model or algorithm. Remember that on the previous exercise we used the decision tree, and right here we're going to use what is called the k-nearest neighbor classification method. And just to give you a little bit insight here, basically what we do to decide or predict the outcome of a response, let's imagine we have this set of data. This is not the flowers, this is another set of data. Imagine that we have 2 features, the X value and the Y value, and this is the representation of all this data, and the color would be the outcome of all these points that we have. All right. The idea with KNN algorithm is that we check for the K nearest value. Let's imagine I want to predict a value that's right where I have my cursor. The idea is to measure the K values closer to this point that I'm trying to predict, and from all those nearer ones, extract the one that's more common and just give it that value to the predicted value. So if let's say that we want to measure with K1, okay? With K1, what I do is I check the one that is closer and I give my prediction that value. So imagine I want to predict the value of a point that's right there. The closer one is this, so I'm going to get a green as an outcome. If I want to evaluate a point that's there, the closer one is probably this red dot, so I'm going to get as an outcome the red value. Okay, this is a representation of what's called the boundary lines of the KNN for K1, okay? And this would be what I would get from any single point. This is the points in here would be, the outcome would be blue, the ones in here would be green, the ones here would be green also, red, etc. Now, if instead of KNN value 1, which means the closest, just the one closest, I deal with the 5 closest, and from the five that are closest to my variable, I try to extract the color that's more common, I would use KNN 5, value of 5. And these are the boundaries that I would get. And as you can see, there's areas which are white, which means that the outcome is tight, okay? The model cannot clearly decide if this area, the outcome should be red or should be blue or should be green, which are the 3 classifications that we have in this problem, okay? If we check here, remember that in here, this area was green with KNN 1, but instead, right here, with KNN 5, we don't have a clear outcome because there's these 2 points that are blue, there's these that are red, this one is green, so the algorithm is not able to decide, all right? So those are little difference between the same, in this case, the same algorithm, but with just playing with one parameter, which is the amount of points that I use to check the closest ones and decide from the value of the closest ones. Okay, now that you get the point of what KNN or K-nearest neighbors algorithm does, we're going to start using with our data, okay? And this is the 4 steps. The first step is import the class that we're going to be using from Scikit-Learn. The second step is create the model or instantiate the class or the estimator. And this is what we're going to do here, all right? So we call the class, which in this case is K-neighbors classifier, and it's on the module neighbors from Scikit-Learn. So that's what we do here. We just import the class, and then on this line down here, we instantiate the class. We just create a variable, and as you see here, I'm going to be use KNN1. I just give the parameter. If I put my cursor here, you see these are all the parameters up here that we can play in this function. And of all those, you see that I can play with n neighbors, weights, etc. One of the beauties of Scikit-Learn is that it has default values. So if we don't add anything, this function is going to use number of K5 instead of K1. This is why I'm, instead of leaving the default values, I'm putting here n neighbors 1 because I want to use the KNN neighbors with 1 as a variable, okay? That's what we do here. We instantiate the variable. Now we have our model stored here, and it's ready to train it. Now before, I'm going to show you here again, printing it, it's going to show me all the variables that I can use, okay? And all this data is, if you go and check the documentation on Scikit-Learn, it's going to tell you what all these parameters mean. But right here, we're only going to be dealing with the n neighbors parameter, which, as you can see, since when we called the function, we gave it the value of 1, it's telling us that it's 1, okay? So now that we have the model already instantiated, we're gonna fit or train our model, and we do this with the function fit and passing the variable x and the variable y. We're passing all the features and the outcomes, and we require, and with this function we train our model, and we just get the same outcome, all right? And but on this variable we have already the fit model, and once we have the fit model, we can make predictions. In this case, we're going to make a prediction of these 4 features. Remember that in this problem we need 4 features. If instead of 4 I pass 3, it's going to give me an error, okay? And I'm just going to require the outcome of one type of flower. In this case, I have one sample that I want to predict that has these measurements for the sepal and these two measurements for the petal. And I require the model to give me an outcome, and it's telling me that it's number 2. If we remember, if we go all the way up, number 2 was Virginica. Okay, so this model is predicting that with these 4 values of features, we would probably be talking about a Virginica species of iris flower. Okay, as you can see, I can predict more than one value. So I'm just creating a variable here called x new that it's got 2 values, 2 flowers with all the features of the 2 flowers, and if I run again the prediction function, is going to give me the outcome of the 2 of them. The first one is a Virginica, and the second one is species number 1, which I forgot. Check again. It's Setosa. Okay, so this is a way to predict just more than one value. All right. Now this is what we get with these 2, let's say, new flowers that we found in the middle of the, of the whatever of the mountain that we captured, and we created a model, and we want to know which species are. Now we're going to do the same, but changing the value of K for the KNN algorithm. And instead of using 1, we're going to use 5. So as you remember, when we instantiate our model, before we pass the value of 1, now we're going to pass it the value of 5, and we're going to fit again the algorithm, and we're going to make predictions. And you saw here that we got a 2 and a 1 as a prediction outcome, and with KNN5, instead I'm getting 1 and 1. Okay, so you start to see that tweaking the values, just one parameter, I'm already getting different outcomes. Okay, now what I can also do is try a different model, and in this case we're going to try another algorithm which is called the logistic regression. Okay, it's an algorithm that uses a kind of curve that it's called the sigmoid function. You can check the information in the documentation of Scikit-Learn, but it's just very common classification model also, although the name regression may bring confusion, but it's a classification algorithm. So what we do here, we just import the class again. In this case, it's in the linear model of the library, and it's called Logistic Regression, and we just instantiate. In this case, we're going to give it the name of logreg, and we pass it. Let me just delete this so you see what happens, and we instantiate the model. Okay, now that we have instantiated, we train it with the fit, passing it the X complete set of 154 features that you see here on this little bubble that appears, and with the outcome, which is shape 150 and just 1. And we make predictions of the same 2 values that we had here, and we got 2 and 1 as an outcome, and 1 and 1 as an outcome of KNN5, 1 and KNN5, and see what we get. Okay, and I'm getting a little message here. It gave me an outcome of 0, 0. As you can see, it's not even either of the outcomes that we had here. Here we had 1, 1, and here we had 2, 1. So I'm getting 0, 0, and I'm getting a little message here, which means that the module just read the final amount of iterations. Iterations reach limit. So if you want to avoid that, which means that basically there is a default number of iterations that the algorithm goes through, and I change here with the max iterations number, and I just increase it to 1,000. And if I run it now, I'm not going to get this error because I'm going to get to the outcome before hitting the maximum number of iterations, although I'm going to get the same outcome, which is 0, 0. Okay? So basically what we've done here is I've shown you 3 different algorithms that we can be using to predict the species of in this case 2 samples of iris flowers that we found, and we want to know what type of species it is. And all of a sudden you realize that there's no there's no final clear solution. Depending on the model that we use, we're getting one outcome or another. Okay, so this is one of the beauties or problems of this beautiful technique, that we have to deal with parameters and play with them. Now again, here we're playing with 150 samples. We need many more samples to have models that really generalize, that make predictions quite accurate and that we can rely on. All right? So on the next exercise, we're gonna make an additional step just to check how we can try to see which of the 3 options would be the best one, okay? And why would we choose one or another to finally make our predictions, right? So let's jump into the 3rd notebook of today, and this is going to be an easy initial way to compare our machine learning models, okay? And again, we have a classification task of predicting the species of an unknown iris, or 2 in this case, or 3, as many as we want. And we use 3 models, KNN1, KNN5, and Logistic Regression. And we need a way to figure out between these models which one is best, okay? Now, we're going to try 2 different ways. The first way is that we're going to get all the data and we're going to train our models with all the data, and then we're going to test that. Okay, we're going to get all the data that we have, train them, and measure that outcome with the data that we have. Okay, so basically we're going to again read the iris data set, and we just directly load it, and we're going to create our 2 variables, the capital X with the features and the lowercase y with our outcomes. Now we're going to start with logistic regression. We're going to upload it from the Scikit-Learn library. We're going to instantiate it as we show you right here. We're going to put a maximum iteration of 500, and we're going to train it, and we're going to make predictions of all the values that we have. Okay, we're going to test it with all the values, and then we're going to predict all the values that we have and check the outcome. All right, so this is what we do here. Okay, and this is the outcome that we have. Now, we're going to store all these predicted values in a new variable that we're going to call y_predicted. Okay, we're going to run again the prediction function with the x values, and then we're going to measure if this is if we have really the 150 that we get with this len. We measure that we have the 150 measurements predicted. Okay, now we're gonna just measure the accuracy, and as before, we will import the metrics module from Scikit-Learn, and we're gonna measure, okay, the accuracy between the y values that we have and the prediction that we got from feeding and training our data, our model, and predicting those y values from the x values. And this is what this function does, okay? And it gives us an outcome of 0.97. So we could say that this logistic regression, it's giving us a right outcome in 97 or 97.3 times out of 100. Okay, so we could say that we have quite a nice, pretty nice accuracy on this logistic regression model algorithm that we used. Now let's do the same with KNN5. All right, so we import again the classifier, we instantiate it, in this case with a value of N5. We train the module with all the data that we have, the variables for the features, the data frame for the features, and the outcome, the labels, and we make predictions of all our data. And then once we have predicted our data and added on the white predicted, we measure the accuracy again with the same function that we had. And right here we see that KNN with a value of 5, the nearest neighbor with a value of 5, is giving us a slightly worse performance compared with the performance of the logistic regression. Now let's make finally evaluate it with a KNN of number 1. And we run it, and what we get here is a perfect value of 1. Now, what happens with this method is that what we're doing here, we're having a problem with this, which basically means that we're using all our data to measure the outcome of the closest data. And we create our model, and then we use the same data that we used to train the model to predict the outcome that we had. But since we're just measuring the closest data, we're basically getting the same outcome that we already have. So as you can see, this method here doesn't have much sense, because we're just measuring the closest data, initial data, which is the data that then we have predicted. So this one doesn't have much sense. Okay, basically this is called the overfit problem. Okay, let me show you this image here. Let's imagine we have these two groups of data. What we want is a model that basically creates this boundary line, which is the black line. And although there are some numbers that are on the other side, this is basically noise. We clearly see that the values that are here, when we want to predict them through our model, we want our model to tell us that they are going to be blue. And the ones that are here, we want our model to tell us that they are going to be red. This value here and this value here is noise. What a model that overfits our data does is create this green line. It tries to match absolutely all the points on our data set. And the problem is that it's not real. We're not getting a real outcome that we want to have when we're measuring real data that we don't have on the sample data. Okay, so this is what is called the overfit problem, and it's a common problem that we have in some of these algorithms, and there's ways to solve that, but it's just to show you on an image what this KNN1 problem is doing. Okay, now in order to avoid this, we do what we did on the very first example of today. We are creating using our data and splitting. Okay, we're splitting between the train and the test data. And basically what we do is we grab our data again, we split it onto groups, we use most of the data to train our model. Once we train our model, we have a small amount of data where we have the outcome to measure. Okay, so once we have trained the model, we use those values that we kept apart to test it, but we know the outcome, and we test it with those values, and we measure the accuracy with those values because we have the outcome. And that's what we're going to do. Okay, so we measure the shape of our variables. Again, it's 150 and 4 for the features, and 150 only for the outcome, the labels. And basically what this we're going to split the data here, and we're going to use this function, train test split, from the model selection of the Scikit-Learn library. And basically what this does is that this is the function here. We create 4 data frames: X train, X test, Y train, and Y test. And basically these two numbers here, this first one is telling me the size of the 2 sets. In this case, I'm using 0.4, and this is just a random number that we can use so we all can have the same value if different people is trying to run through the same problem. If you put a 4 here, if instead of having this number here, I wouldn't use this variable, you may get different outcome, which is not going to be good to measure and get the same data that I'm using. So this is just to make sure that it does the same, it uses the same random number to split. So basically, if we had 5 records of information, okay, with 2 features and 1 response, and we would run this function, we would get 2 groups, the train and the test. The train would have 3 pieces of data or records, and the test would have 2, and then we would get again 2 groups of outcomes, the train and the test. The train would have 3 records and the test would have 2. Okay, this is what we get with this function here. Okay, so once we split the data, what we do is that we train and test with different data, and this way the response values known for the testing set, we have the response values for, we know them, so we can make predictions and evaluate the problem, the outcome, and the quality of the algorithm. Okay, so testing accuracy is a better estimate than training accuracy, which is what we did on the previous problem. Okay, so now here we split it. So we didn't run this cell, that's why we got an error. We're gonna split it, and now that we split it, we're gonna print. And as you see, the train, the X train, has 90 values and the test has 60 values. If instead of this 0.4 I write here a 0.5, and I'm gonna get 75 and 75, because it's 50 for each group. Okay, it's usually better to use most of the data. So let's put here a 0.4 or 0.3, between 60 and 80 for the test, and the rest for the train, excuse me, and the rest for the test. Okay, so we coming back to our values of 90 for training and 60 for testing. Okay, now let's measure if the Y has the same shape. Correct, we have 90 for test, or for train, excuse me, and 60 for test. Okay, so step number 2 is train our model, and remember we instantiate the classifier, and we just fit the fit function. It's going to train it, and we use only the train values. Okay, so that's what we do here, and this is our model is already trained, and now what we're going to do is we're going to predict the test values that we have the outcome. Okay, and we are going to store these values in the Y prediction. And once we have stored the values on the variable, we can use again the accuracy function to measure the outcome, because we have the labels of these test values. And this is what we do here. And with logistic regression, we now get an accuracy of 0.96666. Now, we do exactly the same process with KNN5 and with KNN1, and now you will see we get the same value for KNN5, and now with KNN1, we just don't get 1 anymore, because we are not suffering the problem that we suffer when we are using the whole data frame to make the to train and to make predictions, and now we're getting a 0.95. Okay, now out of these 3 values, we would say from these tests that we made that logistic regression and KNN5 would be both good enough and better, slightly better than KNN1, and we would use either one of these 2. But just to make a final step forward, what we're going to do here is we're going to go through a loop and test all values of K from KNN module or algorithm between 1 and 25 and get the outcome and see and measure the accuracy of all these 25 test or training and training the algorithm and get the outcome, and we're going to append it on this variable that it's going to be called stores. Okay, so that's what we do here. And finally, we call our matplotlib function, and we plot the outcome of the accuracy to check which case are going to give us the best outcome, as this is what we get here. And as you can see, at the very beginning, we get the 95, which is what we were getting here on KNN1, okay? And then we get a better value. On KNN5, we get a 96 that we got here. But if we check from KNN6 to KNN16, more or less, that's where we get the best values, which is 0.984 almost. So from this little experiment or test, we see that KNN values between 6 and 10 or 12 or excuse me, 18 more or less are giving us the best outcome. Okay, so out of all this testing, what we see is that from the 3 algorithms, the 3 or KNN5, KNN1, logistic regression, and making the final test of KNN from 1 to 25, the best outcome is right here. And this is very common. Usually on the edges, we get overfit problems. So usually on the middle range is where we get the best. So what we're going to do is finally use KNN11, which is one of these values. Now that we know exactly what's the parameter, and remember that we have a bunch more parameters, but we're just using the number of closest neighbors as a parameter, that we get the best outcome. Now we're going to, again, finally instantiate our model KNN with 11. We could have used 11, 12, 13, 14, okay, either one of these. We instantiate it, and now that we have finally the best parameter, now we train it with all the data. We don't need to split between tests because we already know, running through all this split, that the best outcome, the best accuracy that we got was KNN 11, 12, 13, 14, and up till 18, okay? So now we train it with all the data because it's more data. It's more 150, it's more than 90 that we were using, and we make the prediction of this case, this value here. And finally, we would get this outcome of 1, okay? So this is just to show you the whole process of running through a bunch of, a data set and trying to use different, in this case, algorithms. In this case, we're using just KNN and logistic regression, and in KNN, tweaking with several parameters, playing with one parameter, in this case with different values of one parameter, to try to measure the best accuracy that we could get. And from all these experiments, we would finally conclude that KNN 11, 12, or so on is the best parameter if we want to use KNN neighbors, which we decided to use that one because with logistic regression, we got initially just up to 96667, and we got a slightly better outcome or accuracy with KNN 11, and then we finally use it to predict. Okay, So one of the downsides of train test split is that it provides high variance between the estimate and the out of sample accuracy, okay? And the k-fold clause, so that means that if instead of using this 4 that we added here, the number 4, that was when we split train and test, where is it, the split, where it is, up here. When we split that, I told you that we used, okay, to create the 2 groups, it uses random data. It randomly picks which records are going to be part of the test and which records are going to be part of the train, okay? Now, if we run this without stating this random state number, it's going to select another set of records for the test and for the train, always keeping 90 and 60. If we run it again, it's going to get a different one. And one of the downsides is that the accuracy changes a lot depending on the records that it selects. This is called, it has a high variance. So in order to work and try to solve that, there's another iteration that we can go, which is called the k-fold cross validation, which basically what it does what we did here, but testing a bunch of different random train and test splits and working with the average of that outcome, okay? And then it's like we have an additional amount of variance reduction to try to get the best accuracy from our data. Okay, it was a long class today. I hope you basically got, you know, the insights of what machine learning can bring you. And just to give you a little, you know, maybe example of what we could do, imagine that we have in crypto, imagine that we have a bunch of people using our HoneySwap products, and we want to try to predict what's going to be the next amount of honey that someone is going to change with wrap ETH, depending on the amount of or the time of the day or the account or stuff like that, because we want to make sure, you know, or we want to try to predict how the the liquidity is going to change depending on the exchanges that run on a specific day. Okay, we could try to use machine learning to try to predict how our liquidity pool is going to change depending on what we have from the past and the accounts that have been, you know, doing some exchanges on those pools, for instance. That could be, you know, a way for someone that's trying to, I don't know, make a bot and try to get the best farming from those pools and use it, trying to evaluate or predict what might be the future use of those using that specific exchange pair during the past. All right. So that's just an example. Those are just three different algorithms that we went through: the decision tree, the logistic regression, and the KNN. There's some more, but I think that you can have more or less some insight of all you can do with machine learning, which is a beautiful field, and I encourage everyone to deeply analyze and study it, because it's really incredible, all the information that you can get, especially when you work with big amounts of data. All right, this is it for today. I don't know if you have any questions. No feedback.
No, thank you, Santi.
I hope you liked it. It was a little more theoretic class. I hope next week we'll dive into the graph and we'll get some information from the graph, and maybe I'm gonna make a mix between the last two classes, and we're gonna try to we're gonna work extracting information from the graph and printing it and generating charts out of that information. Okay, and since it's gonna be we're gonna be using the IDE, we won't be using notebooks. I'll be using PyCharm. You can of course try it on any other IDE that you may be using, like Visual Studio Code or any other. But since we're going to be using a specific library to generate the outcome, which is going to be a web-based outcome, we cannot use a notebook, and hopefully you'll be able to get some insight of how to get information, fetch information from the graph and use it. Okay, we're done for today. I hope to see you all next week, and keep going for the last 2 classes.